Good afternoon, everyone. Well, at least those on the Eastern time zone. Welcome to today's technical webinar on bus protection, one of a series of technical seminars. So please look out for other invites that will be presented in the next couple of weeks on various other interesting topics. Your presenter today, yours truly, is Mike Ramlachan. I'm an application engineer here at GE's Grid Solutions business in the North American region. And I'm coming to you live from sunny Orlando, Florida. Today's topic is focused on bus protection, specifically differential bus protection. I will attempt to present the following topics for the next 35 to 40 minutes or so, and then we'll take questions as time permits. We'll start with an introduction on why bus protection is important, and we'll discuss some typical bus arrangements, including what are their advantages and disadvantages. The discussion will then focus on various bus protection techniques or schemes, and how those are affected by CT saturation, and how we deal with CT saturation issues. I'll go through a brief discussion on some advanced algorithms. I should mention that I will not have a lot of detailed discussion on CT saturation because time just does not permit in the allowed time slot for this presentation. Introduction to bus protection. What are the challenges we face when it comes to protecting a bus zone? A bus is a junction point where sources terminate. Typically in our transmission and distribution, those sources are our transmission and distribution lines. At transmission levels, there can be more than a dozen of these type of terminations or sources. Therefore, if a short circuit occurs on the bus, then there will be multiple sources contributing to the fault current, resulting in very high levels of fault current. This results in damage to the equipment from mechanical stresses on the bus bars, can lead to extreme CT saturation if your CTs are not sized properly, and even if they are sized properly, we could still have large amounts of CT saturation due to DC offset. These can be a safety hazard to personnel due to the high levels of arc flash energy produced. In today's environment, we're very concerned with the personnel safety and our arc flash energy produced. In the following slides, I will explain how we reduce arc flash energy by using bus protection. We need to identify and isolate these faults to minimize their effects. Conversely, maloperation of the bus protection system has other significant impact, including outages to customers, downtime of our processes, which can lead to significant financial impact, and voltage stability levels that can cause other equipment to be adversely impacted. More serious case being widespread system collapse, such as the 2003 Northeast blackout, which fortunately or unfortunately I was part of. I was living in New York City at the time. It was not pleasant in the middle of August when it was the hottest time period of the year. Therefore, we must design a dependable and secure bus protection scheme. This is not always easy, since to enhance one, we will affect the other adversely. Example, increasing dependability, we might have to sacrifice security. For the most part, we try to emphasize security, because we need to keep our customers online. Challenges to bus zone protection. An effective bus zone protection scheme should have flexibility to be applied at many different configurations due to the various bus topologies that are applied. We'll discuss some of the more typical topologies as well as the placements of CTs for bus zone protection. For example, there might be only one bus coupler CT, or for live tank breakers, there might be a dead zone because of the placement of the live tank CT. Now, in North America, I know we don't have a lot of live tank breakers, so most of the installations that at least that I'm aware of in North America are dead tanks, so we don't have this issue so much in North America. Bus reconfiguration is also provides challenges and must be considered. So our bus, whatever bus protection scheme that we select or use in our bus design, should be able to handle all of these challenges. High-speed tripping, specifically tripping in 12 to 24 milliseconds, is advantageous in that it will reduce arc flash energy and minimize equipment damage. Minimizing equipment damage might be in terms of saving a transformer, being able to repair it in a short time period, versus losing the transformer and having to replace the entire transformer, and obviously increasing our downtime. One of the other advantages of using bus protection, it has no impact on system coordination issues. If you attended the previous overcurrent seminar by my director, Terry Smith, you would have seen that coordination can add significant tripping time to our schemes. Bus protection is always in operation, and coordination studies are not required to set and select bus protection systems. Bus protection is always in operation, unlike some of the typical, for example, maintenance switch scheme for reduction of arc flash energy while working in a switchgear. For this scheme, someone needs to physically or manually turn on and off that maintenance switch to go into our arc flash mitigation schemes. With a bus protection, it's always in service, and we don't have to worry about not having arc flash protection or not. And obviously, minimizing damage leads to shorter repair times and less downtime. Bus arrangements and components. One of the more simpler bus arrangements is what we refer to as single bus or single breaker arrangement, which you will find mostly at distribution and lower voltage levels. It offers not a lot of flexibility, actually no flexibility in terms of being able to operate it. If you need to take a bus outage, you need to take all the breakers associated with the bus out of service, so all your sources, all your loads need to be taken out. If there's a fault on the bus, you need to trip all the breakers on that bus, again, taking out all your sources and all your loads. So not a lot of flexibility in this design. Building on the single bus design, we have a multiple bus section design or single breaker with bus tie design, which we see a lot on the industrial applications and industrial sites, commonly referred to as main tie main schemes. These are, again, at some of the lower voltages. It offers limited operational flexibility, so the zone 1 loads and zone 2 loads will basically be able to pick up 50%, 50% each of our load. And the source might be a dual source on zone 1 and a source on zone 2. So if we lose one of the bus zones, we can easily pick up 50% of our load on bus 2. Or if we lose one of our source, we can then pick up the other 50% of our load from the remaining source. So it offers some reliability in the design other than some operational flexibility of being able to maintain one bus while being able to keep the loads in service. Building upon the main tie main scheme is the double bus with a bus tie breaker, which is optionally installed. And this scheme is very common arrangement in the West Coast substations. You find it at transmission and distribution voltage levels. How this scheme works is you can take out any of these breakers from maintenance without affecting any loads in your system. You can take out the bus, one of the buses for maintenance without affecting any rear loads. So for example, if I take out bus 1, I can use my isolators on those breakers. So you can see on each breakers, there's 2 isolators going to each bus zone. So if I remove bus 1 or take an outage in bus 1 for maintenance, I can just open the isolators associated with the breakers from bus 1 and be able to carry my loads from bus 2. A fault on either one of those bus only disconnects the circuits associated with that bus zone. And we can then quickly be able to re-energize those loads by closing the isolator associated with the other zone and opening the isolator on the zone that's faulted. Main and transfer bus schemes. In this scheme, there's basically a transfer bus. Normally, all our loads are being fed. Loads and sources are connected from the main bus. Then for the transfer bus, if we need to take an outage on the main bus, or if there's a fault on the main bus, we can quickly restore our loads and sources by transferring over to the transfer bus. Also, if we need to take a breaker out for maintenance, we can then transfer that load over to the transfer bus and use the bus tie as the breaker for that load. So it offers really good flexibility for taking outages and maintenance and doing maintenance. The breaker and a half bus. So this is one of the most reliable designs that we have in terms of bus topology, used at higher voltage levels. It offers probably the maximum operating flexibility of some of the schemes we've seen. However, the drawback is it requires more breakers. More breakers requires more real estate, so this is a costly bus arrangement in terms of implementation. In this scheme, we have 2 buses, bus 1 and bus 2, and our loads and sources are always connected to both of those buses through the breaker and a half on each section. The loads and sources on the sections are the protection for those are provided by their own protection systems, whereas the bus zone itself is protected by its own bus zone protection. One of the typical bus arrangements that you'll see here in North America is the ring bus at transmission level or high level voltages, 345 kV, 500 kV, and above. So there's a separate, in this, all the sources and loads are connected in a ring format with the breaker separating each section. With this scheme, typically there is not usually a dedicated bus protection system. What protects the bus is the line zone. So whatever line protection is installed also covers the bus. The only drawback with that is if there is a fault and the protection trips for that line section, we might not know right away if the fault was on the bus section or the fault is on the line section. So we might need to do some additional visual inspection. Whereas if you do have a dedicated bus protection system for these ring bus applications, along with the line protection, then we would know right away if there's a bus fault or a line fault. But typically the line protection, because of the economics, you don't have to install additional CTs and additional relays for the bus section. It's more easy to apply this protection by incorporating the bus as part of the line. So now we'll go in through some of the protection techniques that protection schemes that we use to protect buses. We use the differential principle usually for bus protection, and that principle uses Kirchhoff's law for currents. So basically, for sum of all currents entering a node must equal 0, the node in our case being our bus, or more typically current in equals current out principle. The only variation here is how we implement this principle. There's various implementations. We'll talk about each one. The unrestrained differential, the interlocking, a blocking scheme, the high impedance differential, and finally the low impedance percent differential. Our focus will be on the low impedance protection today. We will cover briefly the other types of protection. The unrestrained differential. Basically, this protection is applied by paralleling all the CTs together physically. All of the CTs come into one junction point and they are parallel together at one terminal point. That terminal point then goes into a relay, typically an overcurrent relay. The advantages of this scheme is all you need is an overcurrent relay. So it's very simple to apply this scheme. The disadvantages is we need to match the ratios in all of these CTs. So all of these ratios need to match. If there is a CT that does not have a matching ratio, we might need to install auxiliary CTs to bring that ratio up to match. The other disadvantages, external faults can lead to spurious differential currents. So we usually intentionally delay the scheme to ride through some of those spurious signals. Hence why we have an ANSI 51, which is a time overcurrent scheme, versus a 50, an instantaneous overcurrent. Interlocking or blocking scheme are typically referred more here in North America as zone interlocking. This scheme uses a blocking signal. So all our sources, so in this example, we have one source. All our loads will then be wired to block our source. So if we have a fault in one of the downstream feeders, for example, I'm showing a fault on the feeder on the right, when that relay senses that fault, it sends a blocking signal to tell the source relay, hey, the fault is not on the bus, you should not trip. If the fault is on the bus, the source relay will not receive that blocking signal and it will trip the bus. Some of the advantage of this scheme, very easy again to implement. We're just using the protection that's already there on the feeder relays and the source relays, so we don't need dedicated CTs. It's simple because all we need is instantaneous overcurrent protection. The drawbacks of this scheme is the wiring. Obviously, we need to wire all of these signals back to our source relay, Yep. So there might be multiple wiring that we need to wire back, so terminations and all the wires that we need to run. The other thing is maintainability of this scheme. If we do have a break in one of those wires, there's an issue with one of those wires, we might not know about it until it's too late. We also have to wait for that blocking signal to get there, so we need to allow the downstream relay to see the fault and pick its contact, close its contact up to send the blocking signal back to the upstream device or the source relay. So we need to have some sort of intentional delay to be able to wait for that blocking signal. Conversely, if we don't wait in the time period to get that blocking signal, we could be fooled or tricked into thinking that the fault is on the bus if we don't get that blocking signal in time and trip the bus unnecessarily. In modern microprocessor relays, we can use communication to simplify the scheme a bit. So we can use IC 6150 goose messaging, which is a high-speed peer-to-peer method of communications between various devices. In this case, our IDs or relays. So all we need to do is have a communication cable run out to each of these relays and maybe a switch to get those signals back to the main relay. So we don't have to wire all of those contacts into the main relay. The other advantage of using communication is monitored all the time. So if we lose one of the communication signals or wires or connections for our communications, we will alarm right away and know about it right away, and we will then be able to take the necessary steps to fix or adjust the scheme. High impedance differential. This is the scheme that's been used, a tried and true scheme, I would say, that's been used for a very long time. It's very secure, very reliable scheme. The operating signal, again, like the unrestrained differential scheme that I talked about earlier with the overcurrent, it parallels all the CT to come into either a sensitive current relay or a voltage relay with a resistor across to read the voltage across the resistor, which is usually called our stabilizing resistor. So for an external fault, the currents will circulate in the CT circuit and not through the resistor, so the relay will read close to 0 volts or very minimal amount of voltage. And if there's an external fault, the differential current will then flow into that resistor and creating a high voltage across that resistor. We will then read that high voltage and say it's an internal fault, and it will then trip the protection. The disadvantages of using this scheme is we need dedicated CTs. We need similar ratio CTs, similar accuracy class CTs. Everything has to be dedicated to our scheme, so we cannot use these CTs for anything else other than this high impedance protection. The other drawback is if we do have a problem in the scheme and we need to troubleshoot, it's very difficult to troubleshoot because all the CTs are parallel into one junction point. So we might need to disconnect some of those points to be able to test these CTs individually. Accuracy is also determined by the resistance. So a lot of times to reduce the resistance seen by the CT, we need to run large cables. The low impedance differential. And this is the more popular scheme today if you're doing any new bus protection system. If you're installing a new bus protection scheme, this is probably the scheme you will choose because of its flexibility. In this scheme, how it works is, again, in Kirchhoff's current law, it adds all the currents, what we refer to the differential currents. It adds the currents vectorially to create a differential signal. And then, depending on the relay type, the relay manufacturer, there might be a number of different ways how we calculate the restraint current. Basically, one way is we can add all the magnitudes up to get the restraint currents. Or in some relays, they look at the magnitudes of all the currents and they take the maximum current as the restraint. Once the differential and restraint current is calculated, we then take a percentage of the differential to the restraint, and based on that percentage, we decide to trip or not. So for example, for an internal fault, we should have a high differential and we should have a corresponding high restraint. So our percent differential to slope ratio will be high and we will be able to trip. For an external fault, we should have a low differential signal compared to a high restraint signal. So our differential signal to a restraint signal ratio will be very low so that we will restrain from tripping. Because of this percent differential that we calculate, this scheme is commonly also known as a percent differential scheme. The advantage is no dedicated CTs needed. We don't need to have CTs with the same ratio. These CTs can be reusable for other things, such as breaker failure protection. The relay will take care of the mismatch of the CT ratios. protection of reconfigurable buses is possible, and we'll talk a little bit about that later. As I mentioned, the differential scheme is formed by summation of the differential currents. Ratio matching may not be required, so you might have different ratio CTs. The relay will do the ratio mismatch. For external faults, we can lead to spurious differential signals, but very small spurious differential signals. So the ratio should still be small, so it'll allow us to restrain from tripping. In our typical schemes, like we mentioned, to cope with CT saturation issues, we might have to have some sort of time delay to it. With this scheme, we have various ways of dealing with CT saturation, which we'll talk about. So the advantages of using the low impedance differential: no need for dedicated CTs. In most microprocessor relays, they can deal with a high ratio mismatch. Specifically in the GE relays, we can do with a 32-to-1 mismatch of the CT ratios. And to deal with CT saturation, we have algorithms to deal with that. And specifically, the algorithms we're going to talk about today is CT saturation detection algorithm using a directional principle, and then the dual protection principle, or commonly referred to as a dual slope principle. We had previously talked about the bus topologies, and we mentioned there are certain bus topologies that give us a lot of flexibility in terms of if one bus is out of service, we can switch the breaker from one bus to the other bus that is in service. But by doing that switching, we change the configuration now of our bus scheme, because, for example, breaker A is not part of zone 1 anymore, it's part of zone 2 because we've switched the isolator over. With the low impedance scheme, since all the CTs are coming individually into the relay, all we need is the isolator position to come into the relay, and based on the status of that isolator position, we can switch that breaker from zone 1 to zone 2. So it allows us to have a lot of flexibility in terms of reconfiguration of bus bars. This reconfiguration scheme, I don't see a lot in North America. North America is more of a fixed bus protection scheme, but they're out there. In other parts of the world, the reconfiguration bus bar schemes are more popular because of just the sheer number of sources and loads that come into one bus. As I mentioned, the CTs don't have to be dedicated for this type of bus protection. They can be used for other purposes, such as breaker failure protection. And we could have a distributed architecture where we basically install merging units at the breaker location to basically convert the CT wires from analog into a digital signal, which we can then send over fiber optic to our central unit, which is located in our control room. So with this type of scheme, low impedance scheme, we can do centralized architecture where we wire all the CTs into one relay at a central location, or the distributed architecture where we can convert the CT wires into digital signal and send it fiber optically to a relay. So in modern microprocessor relays, what we try to accomplish in our differential algorithms, specifically for differential algorithms, is obviously we need to have good filtering. So we need to look at just the fundamental component. We need to have fast response because we need to trip as quickly as possible. We need to have good restraining techniques. Restraining techniques meaning specifically for CT saturation, we need to have techniques in place to deal with that, so to restrain from tripping if there's an external fault with extreme CT saturation. And we need to be able to be dealing with the transient issues during switching operations, be able to provide dynamic bus reconfiguration and be able to do that automatically in our relay. we needed to dependably able to detect CT saturation in a fast and reliable manner, and we'll talk a little bit of some of the algorithms that we use to do that today. And we need to have these schemes to be able to be secure and not trip for external faults, especially external faults with CT saturation. And again, as I mentioned, we'll talk about the scheme that we can apply to deal with that very reliably. CT saturation. So before we talk about CT saturation, I do want to mention the dual slope curve. So you could see the red dotted curve. This is typically used in bus protection schemes where we have a slope 1 and a slope 2. As I mentioned, its slope 1 is the differential of the restraint signal. So the lower the differential, the higher the restraint, the more we're going to restrain from tripping. So in our slope 1, or the region 1 of our curve, we expect to be operating normally during normal loading, or when we have DC saturation, DC offset, which causes CT saturation. And in region 2, our high slope, is we are going to be operating it when there is a fault, internal or external. So what happens to a fault trajectory when we have a fault? So basically, we start off at time 0, normally operating. So we have a fault. If our CTs are performing properly, we'll go to time 2 because we'll see an increase in restraint signal with very little increase in differential signal. However, if we have an external fault with CT saturation, what's going to happen is we'll start it again at T0, where we'll be normally operating during loading. Then we'll go briefly to T1. Why briefly? Because during the first couple of milliseconds, at least, the CT will operate properly. It will reproduce the primary currents properly and reliably until it starts to saturate. When the CT starts to saturate, typically about a quarter cycle, then the trajectory will go from T1 to T2, because when the CT starts to saturate, we will see an increase in differential currents. So since we know what our trajectory is going to be, T0, T1, and T2, if we see that sort of trajectory, then we can say, hey, our CT has saturated because we went from an internal to an external fault, external to an internal fault. Our CT has saturated, and we can use that principle to determine whether the CT is saturated. Some of the methods of securing bus differential. We won't talk about the intentional time delay because we mentioned the disadvantages of using that. We talked about the dual slope characteristics. One other principle we'll talk about is the directional principle. So if we talk about the advanced algorithm to handle CT saturation, I mentioned we split the curve into region 1 with a low slope curve, and then region 2 with a high slope curve. That previously mentioned. In region 2, we can reliably detect CT saturation because we know how the characteristics are going to go from T0, T1, and then to T2. So we can reliably detect CT saturation. However, if we're operating in region 1 curve and we have CT saturation due to DC offset, we cannot reliably detect CT saturation in that case because it might be very small. And we will not see a trajectory as going from T0, T1 to T2. We'll see its trajectory just going from T0 to T1 into our operate region. So how do we deal with those cases? So we set the directional flag. The directional flag basically says, hey, if I have an external fault, at least one of my currents will be 180 degrees out of phase from my other currents. If I have an internal fault, all my currents will be in phase with each other, plus or minus 90 degrees of each other. So if, in this case, if we have an external fault, then we will say, hey, my CT directional, they're not indicating an internal fault. So if I have a directional operation in zone 1, I will not operate because my directional flag has not been set. If I have an operation in region 2, if I have high external current, for example, a close-in external fault, I have high fault currents, then I might or might not set my CT saturation flag. If I don't have CT saturation, I don't set the CT saturation flag, then I'm allowed to trip. If I do set the CT saturation flag, saying I have detected CT saturation, then additionally, I want to look at my directional. So if I do have CT saturation, I'm not going to look at if I do have CT saturation, I'm going to look at the directional. If I don't have CT saturation, I don't need to look at the directional flag. And conversely, same for an internal fault. I'm not going to set my CT saturation flag because usually I might or might not set the CT saturation flag, but my directional flag will always be set because all my currents are in phase with each other. So whether I trip on region 1 or region 2, I will have a trip output because my directional will give the permission, whether it's region 1 or region 2. So in conclusion, the dual slope, dual breakpoint castic with the transition between the slope is one technique we use for coping with CT saturation. So we have 2 points of the curve where we slope 1, where we operate normally during DC offset, and then slope 2, when we have high external faults with CT saturation, we increase the slope to deal with that CT saturation. Then we have the CT saturation detection algorithm, which basically looks at the trajectory of the fault going from normal to T0 to T1, and then CT saturation taking me into T1 in the operate region of the curve. Once I see that trajectory, I'll determine that there's a CT saturation, and then I look additionally for the directional flag to be set. Typical response times of our differential busbar protections using low impedance algorithms is about 12 milliseconds plus the contact operate time. And maximum, and I'm talking, these operate times are for a 60 hertz system. So for a 50 hertz system, it will be a little bit slower, obviously. So we're talking about typically 12 to 16 millisecond operate time, then plus your contact operate time, which for standard contact is about 5 milliseconds. So we're looking at about 17 to 21 milliseconds. If we use high-speed output contacts, which are generally less than 0.2 milliseconds, then it adds not any significant delay to our tripping time. And because of using the dual slope characteristic in our CT saturation detection algorithm, we can provide really good stability for external faults, so making our system very reliable and secure.
So our first question of the day is, what is the best type of relay to implement bus differential protection? Well, GE relays, of course, but more specifically within our portfolio, there is the MICOM P74X relay and the UR-B90 or B30 relay. Depending on the number of restraints or the number of breakers that you need or you have on your bus, one or these relays would be the way to go. The B90, which is the UR, which is part of the UR family, which is more popular here in North America, has 2 families, the B30 and the B90. The B30 can do up to an 8 breaker application, whereas the B90 can do up to a 24 breaker application. However, with the B90, because we just can't physically fit, obviously, 24 CT wiring into a single relay, you'll need like at least 3 or 4 boxes in terms of the number of devices to implement the full 24 breaker scheme. Now, you could also, as I mentioned in the presentation, you can also implement a decentralized scheme where you have merging units installed at the CT location, specifically at the breaker locations. And then those merging units will convert the analog signals into digital signals over fiber optic and send them back to the central relay located in our control room. This protocol that we use is the standard IEC 61850 sample value, or 9-2 LE, or 61869-9 instrument transformer standard. So it's a standard, so as long as the relay implements that standard, it should be able to get that merging unit information. The second question that comes to us today is, for a dynamic bus configuration, what happens if the disconnect state is unknown or erroneous? Should the bus differential be blocked? So this is a bit of a loaded question, and it all depends. It depends on protection philosophy of the user, of the utility, whoever is implemented the scheme. I would not recommend blocking any critical protection functions, especially if there is no backup. So in cases, if you have two bus protection schemes backing each other up, then yeah, maybe you want to block if there's a problem with one of the disconnector switch, because what happens in a dynamic scheme, if you don't know the status of the disconnector switch, you don't know which bus that feeder or breaker is connected to, so that might erroneously cause you to calculate differential current when there might not be differential current present. If you have redundancy, then yeah, you might want to think about blocking if you have an issue with your disconnect. So how do you detect issues with your disconnect switch status? You definitely want to wire the A and B contact status from the disconnect. And the relay can then determine, if there's a mismatch between those two, there always should be the opposite, right? If the disconnect is closed, the A contact should be closed and the B contact open. And in the opposite, if the breaker is open, the A contact should be open and the B contact closed. If there is a discrepancy between the two, then you can alarm for that disconnector status alarm. What happens if you do detect a disconnector issue and you don't have any sort of redundant scheme? There's an option to go to the default is protecting the bus as a whole, meaning that you're going to look at all the CTs in and out of the substation, and basically we can refer to it as a check zone. And I'll talk a little bit in the next question. There's a question on check zone, so I'll discuss what a check zone is in just a little bit. However, be aware that if you have a fault on one of the buses, you'll trip both buses in this when you default to this scheme. So the other question is, and follow up to the previous question, is what is check zone and why is it needed? Check zone is an additional security measure that ensures there's an internal fault in the substation or bus arrangement. It's usually employed with dynamic buses. You don't see it employed as much with fixed static buses. So it is usually independent of the isolator status, and it uses independent CTs if those CTs are available. If you don't have independent CTs, then you have no choice. You have to use the same CTs that you're using for your main bus zone differential. So the big part here is it's independent of the isolator status, so it doesn't care if you have isolator status or not. What it's usually used for, it gives the permissive signal to the main bus zone to operate. So basically you're verifying that when your main bus zone has operated, you're verifying that there's actual fault within the bus arrangement as a whole, or the substation as a whole. But to implement the check zone, obviously, you need all of those CT inputs to come into the relay. And that's pretty easy to do if you have a decentralized or centralized scheme, if you have the appropriate relay to handle the amount of breakers. Up, as I mentioned, for the B90, we could do up to 24 breakers. The fourth question here is, can a bus protection relay be used when there are different CT ratios, either the primary rating or the secondary rating? The simple answer is yes, definitely. You could do this in modern breaker processor relays, and specifically with our GE, UMOR, and MICOM relays. The more complicated answer to this is how the relay accomplishes this. We just don't have enough time to go into the details how it does it, so I'll try to summarize as much as I can. What the relay does, it establishes a common per unit base, converts those common the different ratios, secondary ratios and primary ratios, to a common per unit base, and then it performs the differential calculation on this per unit. So basically, all the CTs are scaled to a common base. So in effect, it does not matter if the CT primary secondary ratios are not the same, the relay will take care of it. So that's one of the, I should mention this is for the low impedance bus scheme. This does not apply to the unrestrained or the high impedance bus scheme. So this is very important. When you're implementing this, you need to use the low impedance bus scheme, or if you want to have different ratio CTs, you need to implement the low impedance bus schemes. Otherwise, you'll be having to install a lot of aux CTs. Aux CTs installed in the bus differential scheme come with their own set of problems and headaches that you'll have to deal with. So I definitely don't recommend installing aux relays unless you really need to. Both the UR being our universal relay, both the UR and the MICOM relay allow combinations of 5 or 1 amp rated CT secondaries inputs. So we do not need to specify ahead of time what secondary rated CT when you're designing your system or selecting the order code for the relay. Each CT input comes with 3 terminal blocks in the back of the relay. One's a common, one's a 5 amp, and one's the 1 amp. So depending on what the secondary rating of your CT is, you would connect it to the appropriate terminal block at the back of the relay for the 1 amp or 5 amp. And then there's a software setting in the relay to select what you're connected to in the back of the relay, the 1 amp or the 5 amp. As far as the primary CT ratio, you can go up to a scale mismatch of 32 in the relay, so you can have a 500 to 5 CT to all the way to a 4,000 or even 6,000 to 5 CT. So it can handle a lot of mismatch within the CT, and you will not sacrifice any dependability or security in the scheme. So our fifth question here comes, can the bus relay detect an open or grounded CT condition and alarm? Yes, it's definitely something that we've implemented in our relays. There is an included CT trouble setting, which is essentially a low set or sensitive bus differential zone. This element will pick up on CT issues since a low differential current will be established if a CT is grounded or open circuited. As we know, open circuit CTs is a safety issue, so we definitely want to detect those issues and alarm or do something about them so that we know those issues exist before personnel go into the panel and can cause high voltages. Open CTs can cause high voltages, which if a personnel is next to it or touches that high voltage can cause serious personal injury. This function can be set to alarm or block the main differential, but as I previously mentioned, I personally don't like blocking protection. I would rather alarm, I would rather trip erroneously than to block when there's an actual fault. Here, another question. How does one calculate and select the correct MOV and stabilizing resistor for high impedance bus differential? As I mentioned in the webinar today, the two different bus differential schemes are high impedance and low impedance bus differential. The high impedance is basically paralleling all the CTs. It's very easy to implement because all you need to do is parallel the CTs. You can support a large number of breakers because it doesn't really matter how many breakers you have as long as they're parallel into one junction point. The limitation is how many cables can you land on those terminal blocks. It then goes into the high impedance relay, and to make the scheme more secure, we usually put a stabilizing resistor in the path of that circuit. So for during loading conditions or an external fault, the current circulates within the CT circuit. There might be some spillover current. Obviously, CT ratios, CTs are not the most accurate things, especially when you're talking about fault currents. The IEEE minimum requirements for a relay class CT is 10% accuracy. So you can get a lot of differential current, especially if you have large external faults, large close-in external fault. So you might have some differential current. So that stabilizing resistor is there. So when you have those spillover currents, it goes into the stabilizing resistor. It creates a voltage drop across the resistor. And if it's a very small spillover current, the voltage drop is very small. The high impedance relay sees that it's a low voltage signal. It will restrain from operating. However, if there's an internal fault, then all of the fault current will flow into that stabilizing resistor, creating a high voltage across that resistor and cause the relay to operate on that high voltage. But what happens when you have really high currents or high short circuit currents is that that voltage drop across the resistor can damage the resistor and damage the relay coil. So to prevent that from happening, what you do is you have a nonlinear resistor or an MOV across the relay coil to protect it from these high voltages. So when it detects high voltages, it basically shorts out the circuit to ground to bleed out that high voltage so that it does not damage the high impedance. The reason I picked this question is I do want to mention that there's some thought into designing and selecting the value of that stabilizing resistor, the impedance value, resistant value of that stabilizing resistor, and the type of MOV or nonlinear resistor you need to protect the relay coil from over voltages. So you should dedicate time to calculate and design those appropriately and select those appropriately. And the selection and design of those will depend on your system conditions, your power system conditions, your short circuit current, both internal and external. The impedances, not the impedance, the resistance of your CT circuits going from the CT panel out to the relay of all your CT circuits. However, we do have tools that help you to analyze this data and to be able to select the appropriate impedances and the voltage, the MOV voltage that needs to be protected. The seventh question here, can we use internal breaker failure function of bus differential relays to replace dedicated breaker failure relay? Yes, certainly. Both the MICOM and the UR relays have dedicated built-in breaker failure elements that you can use. This can actually simplify your design because the signals that you use to detect whether a breaker is open or closed, specifically the CT signals, are already wired into the bus differential. So it's common that if those CTs are already coming in there, then why not use them also for breaker failure so that you simplify your design. You don't need another external box to do it. Obviously, the consideration is redundancy in your design too, right? If you might need some sort of backup device that if there's a failure in the bus differential relay that you've lost your bus protection and your breaker failure protection, so you might want to think about some redundancy in your design as a backup to that. There are application design consideration when implementing this scheme, and specifically one of the examples I mentioned is the redundancy in the scheme, whether you don't want to lose one relay and lose both your main protection and your backup protection, backup being your breaker failure protection. With that, we can probably take another question here. Can metering CTs be connected to the B90 UR relay? Definitely, you don't want to do that. Metering CTs are not sized appropriate to handle short circuit fault current. They're sized to be very accurate for loading conditions. When you have a short circuit, your short circuit current can be 20 times your loading current. So the metering CTs are not designed to handle that type of current, and they will immediately go into saturation. They'll be completely saturated, and that will cause the differential element to not operate appropriately. So you definitely don't want to implement metering CTs in your differential scheme. One other question I can take here. So 24 breaker or 24 CT inputs, is that just 8? Or, so when I say 24, when I talked about the B90, so I'm going to rephrase the question a bit, sorry. What I think the question is asking, he's saying when I say 24, that the B90 can handle up to 24 restraints, am I talking about 24 CT, single-phase CT inputs, or 24 breaker inputs? I'm talking about 24 breaker inputs, or 24 three-phase inputs. So 24 times 3, I can't do math anymore, how much that comes out to, but it's 24 three-phase inputs that the B30 can handle. So with that, I want to thank everybody for attending the webinar today. If you have any questions after the webinar, please, you can also shoot them out to us, and I'll hand it over to Tessine to finish off for us.
Thank you, Mike, and thank you everyone for attending. We look forward to seeing you again at our next Tech Talk. This concludes today's webinar. Have a wonderful rest of your day. Thank you.